Okay, so it's a great pleasure to have the person who is the new Warwick maestro, the co-director, right? So and he's going to be talking about a direct approach for sparse quadratic discriminant analysis. Sorry about that. Thank you. Okay, Chenlei, thank you.
Thank you. Thank you, Jim, for the introduction. So I'm going to talk about a recently submitted paper called the Quda, and this is joined with two brilliant individuals. So I guess the motivation for this talk is based on the OxWaSP program. We are talking about statistical sciences for 21st century, data-intensive environments and large-scale models. What does this mean, right? I guess we are collecting a huge amount of data sets, and these data sets arise in a number of applied areas. For example, you can talk about brain imaging, astronomy, engineering, internet, social sciences. And for some of the Warwick and Oxford people here, we'll be looking at some kind of omics data. And you can talk about, for example, genomics, proteomics. And if you care about what politicians have to say about the current world, you can also include the words such as economics into this picture, right? So really, I think there is a paradigm shift in data analysis in the sense that we are moving away from hypothesis-driven data research to more data-driven research in the sense that data are collected first before questions are asked. To give you a very simple example, if you are doing online transaction, all kinds of data collected, people would have no idea what questions they would pose at the very beginning. Okay, so really, we are having a huge amount of data sets, and a characteristic of this data sets is that typically the number of the features or the variables are huge in comparison with the number of the observations we collect. Okay? So if you think about your data, if you organize your data in a matrix with the columns representing the variables and the rows representing the observations, then we have a fat data to start with. Okay? Now, of course, life would have been much easier if your variables act marginally on the response variable of interest. You can look at each individual variable separately to figure out what's the relation. But of course, this is not the case in practice. So features often interact in interesting ways. And the aim of this talk is to introduce a very simple model for big data classification. Okay, now, for those of you who are not, especially for our students who are not familiar with classification, here is a one-slide introduction to classification. So I simulated two populations of observations. Okay, I coded them using either the blue color or the red color. And together with each observation, I observe two variables. Okay? I have x1 and x2. Now, for the moment, let's think about x1 as some measurements possibly related to, let's say, blood tests, and x2 as some measurements related to, let's say, ultrasound scan. Okay? Now, the idea here is that you collect a bunch of observations, and at the end of the day, when you have a new patient or new subject coming in, you want to classify this new subject either to the blue class or the red class. Okay? Now, of course, you may ask why you can just measure the status of this subject without going through these two kinds of tests. But oftentimes, it is the case that it can be expensive or sometimes even invasive to medically diagnosis, for example, the disease status of the subject. For example, if you are looking at the cancer status, right? So it would be just much easier to measure these two variables, okay, now to figure out what disease status this particular subject would belong to, right? So here I also draw basically two lines here. Now this is the classification boundary of the linear discriminant analysis rule, which is basically a straight line. And you can also talk about more complicated decision boundaries, such as a curve. And by the way, this is a quadratic function of these two variables, and this is a linear function of the two variables. Okay? So let's look at the mathematics of this problem more closely. So we can consider observations from two classes, and we can assume that observations from class 1 follow some kind of a multivariate normal distribution, and observations from the other class follow another normal multivariate normal distribution. Now, of course, in practice, we are going to look at much more complicated situations in which we have much more variables to worry about, not just the two variables to worry about. Okay, so here mu1 and mu2 are the two mean vectors, p-dimensional, and the sigma1 and sigma2 are the two covariance matrices. Okay? Now, given the data set, as I said, the goal is to classify a future observation, let's say Z, to one of the two classes, such that the misclassification error is made as small as possible, right? Okay? So that's the setup of the problem. Now, of course, if you know everything, if you know the distribution, if you know the prior distributions, and so on, okay, there exists an optimum rule. The optimum Bayes rule basically classifies a new observation into the class which has the larger posterior probability. Now, mathematically speaking, you classify this new observation to class 1 if the posterior probability for class 1 is bigger. Okay? Now, if these two covariance matrices are the same, the procedure becomes LDA. Otherwise, it is the QDA. That's the focus of the talk. Okay? Okay, so here is the outline of the talk. I will introduce the problem first, and then I'm going to talk about the Quda procedure, followed by some simulation studies and the two data analysis. If we have time, I'm going to mention some theory, and finally, this talk will end up with some discussion. Okay? So again, we are going to look at the optimum Bayes rule. Turns out that the Bayes discriminant function consists of all the z's satisfying this function. So this is basically what I draw in this figure. Okay, I found basically all the z's such that that the two probabilities are equal. Okay, so we can look at the classification boundary. Okay, by working out these two probabilities. Now it turns out that the discriminant function can be denoted in this form. Well, this mu is the mean of the two centroids, the average of the two centroids, mu1 and mu2. Okay? And this omega is the difference of the two precision matrices. Okay? So this is another parameter. And we can also look at this delta parameter, which is here, as well as another parameter, which is basically a scalar written in this form. Okay? And by the way, again, this classification rule reduces to that of the LDA if the two covariance matrices are the same. Okay, so this is a very simple setup, and we have a discriminant function of this form. Okay, so just a few remarks. Okay, so if you look at the discriminant function more closely, well, you can see this as some sort of a two-way interaction model as in linear regression. Okay, and that's why we name it QDA. Okay. Now, to appreciate this function more, we can understand that the non-zero entries in this omega matrix as the important interactions. So if you have a non-zero here, it means that the corresponding entries in Z have interactions. Okay? Now, similarly, you can also understand the non-zeros in this delta vector as the important May effects. So in some sense, this model, this classification boundary can be understood as some kinds of interaction models. And the goal, of course, is to figure out what interactions are important, what May effects are important. Okay, that's the goal of the research. Okay, now of course we don't have the oracle; we only have a data set. So let's suppose we have observations from x1 up to xm sub 1 from class 1 and the y's from class 2. Okay. Now we can go ahead to estimate all the unknown parameters needed in our classification rule, right? So that's exactly what we can do. So what we can do is to estimate mu1 by mu1 hat by taking the average, simple sample average, and the mu2 as the simple sample average, okay? And similarly, we can estimate the sample covariance matrices sigma 1 as well as sigma 2 using the no sample variance estimates, right? And finally, we can also estimate the prior probabilities, right? Okay, so it's quite simple. We estimate all the unknown parameters in our probability density functions as well as the prior probabilities. And after that, we can plug in all the estimated parameters into our rule, right? So and then the job is done. Okay. So basically, that's what we can do. So we plug in all the sample estimates, right, into the classification rule such that all the parameters can be estimated, right? So here are the parameters, okay? So this is fine, and this is a classical QDA, okay? Right, what happens if you have a data set where the number of the features is much larger than the sample size, right? So that's what happens. So let's look at this case more closely. So in this case, the dimensionality, which is denoted as P, is much larger than the sample sizes, okay, N1 and N2. So here I'm going to pose a few questions. Okay, so can we still use this mu hat to estimate mu? This is for our OxWaSP students. Yes, it's fine, right? So you have one sample estimate, you have another sample estimate, take the average, it looks fine. Okay. Now what about omega here? So again, you have a data set where the dimensionality is much larger than N1 and N2. Okay, let's suppose we go back to the sample estimates as I had here. Okay, I plug them into my expression of omega. Can I do that? No, if the dimensionality is larger than the sample size, if you look at the sample estimate, this guy is not going to be invertible. This guy is not going to be invertible either. So if you are inverting two degenerate matrices, you are not going to get anything meaningful. So having said that, this plugin estimate is not useful if you have a large dimensionality. Okay, and the same thing can be said about this delta vector as well, right? Okay. If this is degenerate, you are not going to be able to invert it. Okay. Now finally, for this eta parameter, probably it's okay. This is a scalar. So if you have a scalar, you can always use some cross-validation based procedure to determine it because it's a single scalar. Okay, you don't have to worry about this parameter very much. So I guess the discussion here is that well, if you look at the 4 parameters that are needed for the discriminant rule, okay, we need to estimate sigma and delta. We have 2 parameters to worry about. These 2 parameters are already taken care of. Okay, so that's the emphasis. Yes, Mark.
Yeah, don't you have to worry about eta too because omega comes into play?
Exactly. Yep. But it turns out that this is a scalar. So at the end of the day, you can just use some a grid search to find it. It doesn't matter, right? But of course, if you want to estimate it, you have to estimate, for example, the determinant of this guy, determinant of this guy, as well as this guy. So that's going to be quite complicated. So we decided to use just a grid search to nail down the value of it. Okay. So I guess the discussion leads to the estimation of 2 parameters, omega and the delta, right? Now of course, if you think about the problem, well, we have a large dimensionality. The number of the parameters in omega scales quadratically with the dimensionality, right? We would have p squared divided by 2, roughly, parameters to worry about, right? So if you don't have a sufficient large enough sample size, there's nothing you can do, right? So now a convenient assumption in this context is to assume some kind of a structure for this omega matrix. And in particular, we are going to assume this omega matrix is sparse. That comes back to my original comment in that, non-zero entries in this omega matrix correspond to important interactions. And if we can identify those important interactions, and that's going to give something meaningful, hopefully. Okay? So that's exactly what we are going to do. We are going to assume that this omega matrix is sparse, and we are going to estimate it. Okay? Now, of course, we are not going to make any other assumptions about the structure of sigma 1 or sigma 2. We are going to just look at this sigma matrix directly. So as one way to proceed, let's notice some simple relationship. If you pre-multiply this omega by sigma 2 and post-multiply it by sigma 1, you will notice that the product is basically sigma 1 minus sigma 2. Now the trick here is to make up an artificial loss function such that this loss function is minimized when this omega satisfies this relationship. Okay, so you come up with a loss function, and this loss function can be written in this way. Okay. Okay. Now again, the point here is that to make sure that the minimizer of this loss function is the omega matrix we want to find out. Okay. So it is as simple as that. Okay. Now, of course, if we assume that this omega matrix is sparse, we can add a lasso type of a penalty to it. Now, the simple way to do it is to add something like this. This is nothing but the sum of the absolute values of the entries in this omega matrix. Okay. Notice that this is a convex optimization problem in the sense if you look at the loss function, if you take if you compute the Hessian of this loss function, it's going to be a non-negative. It's going to be a positive definite function. Okay, and this guy is also convex in terms of its parameters. So this is a positive. Sorry, this is a convex optimization problem. And if you have some algorithm to solve it, the solution is guaranteed to be unique. Okay. So that's exactly what we want to do. And by the way, in practice, we replace the oracle parameters by their sample estimates. Okay, so this is what you can do, right, in practice, because omega 1 and omega 2 wouldn't be known to us, right? Okay, but if we have a data set, we can estimate these two guys. Okay, so this is the way to estimate the omega parameter. Okay.
Excuse me.
Yes.
Any information for the loss function?
Yes, as I said, you want to make sure that, well, this is the form of the omega parameter, right? Okay. When you come up with a loss function, you want to make sure that when you minimize it, the loss function, the solution satisfies this equality. Okay. So it's just natural to come up with some kind of a quadratic form for this omega parameter. Okay. And the reason we have a quadratic form is because quadratic form is usually easy to minimize. Okay, you don't want to go to, for example, log determinant type of criterion, which can be difficult to handle. Okay. So this is as simple as that. So we have a convex optimization problem to solve. Okay. And as I said, if it's convex, there are many good, well-tested algorithms for doing it. Okay, so here is one I took from the literature. It's called the Adam algorithm. Okay, so the way to think about it is that, well, if you look at this optimization problem, well, if you want to solve it, you can't really take a derivative with respect to this matrix parameter omega. It's difficult. So to proceed, what you do is to replace this omega matrix in the penalty part by another matrix. Okay? And you make an additional equality constraint. It doesn't change the form of the problem, right? It's the same problem. Okay? And now you can form what is so-called the augmented Lagrangian. Okay? By using a Lagrangian multipliers for this equality, and in addition, you add a quadratic penalty to the difference. So this is different from the usual Lagrangian multiplier method, right? Okay, if you are looking at the usual Lagrangian multiplier method, we are looking at this form, right, without the last expression, right? Okay. So it turns out that, well, if you look at the augmented Lagrangian, what you need to do is to optimize one parameter at a time. And here we have 3 parameters to worry about. We have the original omega here, and I introduced one additional parameter psi. Okay. And also we have this Lagrangian multiplier to worry about. So really, you can iteratively update the 3 parameters in this form. Now, the nice thing about this Adam algorithm is that for every step of the algorithm, you would end up with a closed form solution for each of the parameters you want to minimize over. Okay, so that's exactly what I want to say about this. Okay. So it turns out, the solutions for these 3 steps all admit closed forms. Okay, so and here I just listed the exact procedure to update the procedures. Okay, and it's very easy to code up. Okay, And let's look at the linear index delta, right? As I said, the non-zeros in this delta vector correspond to important May effects. And let's see how we can obtain an estimate of this delta vector. So recall again, this delta has this form. Okay? Now, of course, we don't want to estimate sigma 1 inverse or sigma 2 inverse. Okay? We don't want to make any assumption about sigma 1 or sigma 1 inverse, sigma 2 or sigma 2 inverse. Okay? So what we would like to do is to, again, use some simple manipulation by pre-multiply this delta vector by a matrix such that the right-hand side of it has a null form. What I mean is that we can replace mu1, mu2 by their sample estimates. We can replace sigma 1 and sigma 2 by their sample estimates. And then we can replace omega by the omega estimates we just obtained. Okay, so if you look at this, using the same trick again, the lasso trick as I introduced just now, we can form a quadratic loss function. And if we can impose some kind of sparsity assumption on this delta vector, we can add a lasso penalty to it. Now again, lasso penalty means this is the sum of the absolute values of its components. Okay? So we have a very nice formulation, and there are tons of algorithms to solve it, right? So I don't have to worry about this optimization problem because there are just too many algorithms for doing it. Okay? Now, any question? Now we have the two estimates in place, right? Omega and the delta, so we can do this. Okay? Yes.
These two can be done independent of each other because delta is not a function of omega at all.
That's right. Yeah. So we estimate omega first, but delta depends on omega in this way. Okay. Okay. So I plug in the estimated omega for estimating delta, as you can see here. I needed omega.
You run it first for omega, then plug it in there.
That's right. That's right. Yeah. That's right. Yeah. That's right. I guess a little bit short of time, so I will skip the literature review, and I will also skip the simulation part. It suffices to say that for many different scenarios, this Quda method outperforms its competitors. Okay, so let's look at the two data analysis. Okay, and I think they are quite interesting. So the first data analysis is taken from a website called Quora. Okay, so this is a website about question and answer. So a community of users basically ask, answer, check, questions basically. So this is a data challenge basically available from this website. And for this data set, we have about 4,500 observations, and we have 20 features. This is not a high-dimensional problem, by the way. We just want to see how our approach performs in comparison to some of the traditional approaches, such as LDA and QDA. Okay? Now, of course, the goal of this challenge is to automatically classify a new answer based on these 220 features. Okay? Now, if you look at LDA and QDA, it turns out LDA vastly outperforms QDA. So probably at this stage, you will just say, well, probably I will just be happy with LDA. I'm going to go with LDA. Now, nothing can stop you from using other approaches. For example, this penalized logistic regression. It improves the performance a little bit. Okay? Now, if you look at those quadratic classifiers, for example, here, penalized logistic regression with interactions included, you can see that actually the performance even further. And finally, the Quda method actually performs the best. Okay, and let's look at a high-dimensional problem. Okay, well, we are looking at the prostate cancer data taken from this paper, and here we have about 100 patients, and here we are going to look at P genes that are possibly related to the disease status. Okay, so we have to motivate this data analysis, we look at the marginal densities of many genes. For example, if you plot the marginal densities of the gene 118 and the gene 182, if you look at the kernel density estimates of these two genes, you can see that actually the two densities are quite close, meaning that if you only look at the main effects, probably you are not going to be looking at, probably neither of them would be useful in classifying these two classes of a patient, classes of observations. But if you look at a graph, this is similar to the first graph I showed you. So here I have, the first gene and the second gene. If you look at it more carefully, you will find out that all the blue dots lie predominantly in this triangle, and all the red dots lie predominantly in this triangle, indicating that there's some interaction going on. Okay. So really, again, we did this comparison. It turns out, again, the Quda method outperforms its competitors oftentimes by a huge margin. Okay. So how many more minutes do I have, Jim?
6.
Okay, good. So yeah, so if you look at the performance, I mean, it outperforms all the other procedures. Okay. Now, of course, we also have some theory behind it. I will skip some of the slides here. It suffices to say that if all the assumptions are satisfied, then our approach will perform well in terms of estimating the true parameter omega as well as the true linear index delta. Now, more interesting, you can also look at the misclassification rate. Okay, let me skip this. Okay, so the misclassification rate, misclassification happens if you classify an observation from the blue class to the red class, or from the red class to the blue class. So mathematically speaking, okay, if you have an observation from the from the red class, and if you classify it to the blue class, then you have a probability like this. Okay, it comes from the blue class, but you classify it to the red class, or it comes from the red class, but you classify it to the other class. Okay, so this is a theoretical Bayes risk, which you can calculate if you know the probability density function of the two classes. Okay. Now, for our rule, we can also come up with a sample estimates of it, which is denoted as this. Now, again, if you have a blue observation, you classify it to the red class, you have an error like this, and so on. Okay, so these two can be characterized in some sense. Now, it turns out that, again, if you are able to make some reasonable assumptions, it turns out that the Bayes risk and the misclassification rate of the Quda rule are very close in some statistical sense. Okay. Right. So I think I will skip this again. So I will briefly discuss the future work of it. Well, okay. We have lots of room to develop old simple models for the 21st century data, such as this QTA. Okay, we can take it off the shelf and we scale it up, and we look at the new ways to tackle it. Okay, and well, my research tends to blend methodology, computation theory, and applications. Okay, now to OxWaSP students, I welcome you to talk to me about a possible project. And by the way, this paper was just submitted last week. Okay, so that's the end of my talk, and thank you.
Thank you. Do we have any questions? Yes.
So your original classification problem, if you look at it from a decision theoretic standpoint,
Right.
and say misclassification in one direction might be a lot
That's right.
less desirable
That's
than
right.
in the other direction.
That's right.
How much does this problem change? Like, is it just the
You-
eta value that changes?
You
so you're-
probably wouldn't change much
Yeah,
because
exactly.
you're right. So you just have to add different weights to different
Yeah.
misclassification errors,
so,
right?
So a lot of this stuff will carry over.
Exactly. I think exactly. You can add weights to the two classes.
So it's just a matter of reweighing and then
Exactly.
everything works out.
Exactly. Yeah.
Thank you.
Exactly. Yeah.